Okay, thank you everybody for joining the beginning class. Jan Simon will be our lead presenter today. And Jan Simon, please go ahead.
All right, welcome everyone. This is the beginner class of the Yocto Project Summit. David and I will lead you through the class today. I will do the first half, David will do the second half. The presentation is in a Google Doc, and you can find it under this link here. And at the end, we will also attach a PDF to the pre-talks to the calendar page. What's all of this about? So the Yocto project helps you to create an embedded Linux distribution, right? We can do that for essentially any device for which we have a board support package, a board support layer, and we have plenty of options to do so. And this training here will kind of give you a quick intro, kind of drinking from the fire hose, and get you up to speed. Let's first talk a bit about the Yocto project and what all of this is. In principle, it is a collection of tools and methods that allow us to do all of this. We can do builds for the usual, like off-the-shelf boards, being that boards from certain vendors, being that popular community boards, pick your poison. And what it lets you do is it lets you adjust a lot of knobs and customize it to your needs, to your liking. So it's not a fixed set here. Take this. It lets you customize, let's say, almost everything. We do support a wide range of architectures ranging from the x86, ARM, MIPS, Power, RISC-V. There are maybe a few others here and there. We do base on the technology and foundation of the OpenEmbedded project, which provides and develops the core. We work with layers, which is great because we can reuse components or swap out components. Yeah, we can use the base layers, add another BSP on top, replace that for a new board, and so on. While at the very top, we have, let's say, our own application. So we are very flexible. Now, what is the Yocto project? The Yocto project is an umbrella organization. It's hosted by the Linux Foundation, which hosts Linux kernel and maybe other projects meanwhile. It's a membership-based approach, as you have heard in the session from Andy just before, and they support the project through their membership duties and make sure that we can develop the project further. The project co-maintains parts with the OpenEmbedded project, so they collaborate on these. The governance of the Yocto project, as organized within the Linux Foundation, there is a split governance model. So there is the advisory board, which makes the financial decisions and the basically rough direction. And there is the technical leadership, which make the technical decisions. The Yocto project has a couple of members. There are multiple tiers, platinum members, and and also gold and silver members, as you have seen already. Okay, now we start with the fire hose. First, if I'll probably take a talk fast. If you have questions, then stop me. That's what I usually say when doing these classes. Otherwise, I will make short after the chapters. All right. So the Yocto project will build packages. So a piece of software that we want to run on our board, essentially we will produce a package out of it. Yeah. And from a set of packages, we can construct a bootable image. This is much like any other distro essentially does it. And there are different packaging formats that are popular, RPM, DEB, and IPKG. Now, regardless of the formats, right, we produce, compile the software, we package it up in some form, and then from there, we produce the image. That's the rough workflow. The Yocto project itself follows a 6-month release cadence. And you see on the next slide here that it is kind of every April and every October, plus minus, but every half year, every 6 months, there is a new release like clockwork. I highlighted 2 here. Those are our current active LTS releases. They are considered stable releases and they are supported for a time frame of 4 years currently. So what we do when we prepare for releases, that we take the latest stable kernel, the latest stable tool chain, the latest version, released version of each package that we have in the layers, and basically packet upref to that, run verification, and add new documentation. There are additional tools which we'll talk about later. One is the SDKs, DevTool, and Toaster, which is also part of the Yocto project. Let's take a look at OpenEmbedded Core. So, as I said, Yocto is a set of components. One of them is OpenEmbedded Core. What is this now? Well, this is metadata. Yeah, this is descriptions of how to create the binaries of the different applications here, the different programs, and we call them recipes, right? So we have about 800 core recipes, and those are a foundation. This is stuff that more or less everyone needs if you want to create a bootable image. Not all of what is in here ends up on the image. There are parts, you need a compiler, you need additional helpers. Those only run on your build machine, for example, right? And other bits end up on the target. This collection also has support for graphics, networking, kernel, debug tooling, and more. So this is kind of the subset that allows you to do an image, which also includes graphics. OpenEmbedded, the OpenEmbedded project, co-maintains the core build system, which consists out of the metadata, we just looked at that, and Bitbake. Bitbake is the tool that can parse this metadata and execute the necessary steps. Yeah. There is also the OpenEmbedded layer index, which we will see later on. And there you can see a big list of layers that can be used. Now, what exactly is Bitbake? Bitbake is the build engine. It's written in Python. It essentially reads the metadata from all of these recipes, right? Determines what needs to be done, what are the dependencies, what are the dependencies of those dependencies, and so on, and so on, and so on. And in the end, we have basically a chain of tasks, a chain of events that needs to be executed. And then it schedules those tasks, runs all the builds, and in the end, you have a ready image. Yeah. On the other side, the metadata, which we structure in layers, is basically a collection of recipes, which tell Bitbake what should be done for a certain piece of software. Now, Poky is what we call a reference distribution. I already said you have a lot of knobs that you can modify, and Poky is basically one selection of the different knobs that is bootable, that the Yocto project runs CI on. So this is kind of a known working reference for us. There is a known Git repo, which you can find here. And it basically consists out of OpenEmbedded core in the subfolder meta. There is MetaPoky and MetaYocto BSP. So there is already a kind of a stacking of layers. It's a starting point, right? It's a known good working starting point that we can use and pick up for our own projects. So in detail, part of Poky is the Bitbake tool, right? So it comes as part of the bundle. We have a couple of build scripts, infrastructure helpers that come with it. We have the essential set of recipes as part of OE core. We have the sample or the reference distribution policy in MetaPoky. We have a couple of BSPs that come by default. We call them reference BSPs. And we have the Yocto project documentation, which you find under docs.yoctoproject.org, which are a very good resource. Now, big picture, putting things all together. The Yocto project is the place to collaborate in a large scale. OpenEmbedded as a technical partner, a sister project, is basically providing the metadata. Bitbake is the build tool, and we have a reference distro that we know is working, right? And that we can go and tweak to our needs. For simplicity, Poky also contains Bitbake and OE core. Now let's take a quick look at what's going on when we actually execute a build. On the left side, we have all inputs, right? So we have the, oops, no, no, no. Did I do? Do you still see my screen? Something went black. What's wrong now? Let me reshare the screen. Just a second. Okay, there we go. Reshare.
Okay, I see your slides.
Okay, yeah, that's better. Yeah, something went black on my screen, so I just quickly reshared. Okay. Looked like an overlay from Zoom. Anyway, okay. So left side, the inputs. So it's your user configuration. So your choices, your custom settings, right? It's the recipes, the metadata that are part of the project. Possible BSPs bring their own configuration snippets, and there could be configuration by policies as well, or built-in policies, depending on what you choose. With all of these inputs, right, Bitbake reads all the recipes, parses them, and then it needs to get all the sources. Yeah, we call that fetch. This is the fetch task. Then we essentially, there is another step in between. We need to unpack, right? Then we need to patch. We need to do the configuration steps. We need to do the compilation steps and so on, all in here. After that, we have the binary representation in here, right? That gets packaged up in the chosen format. And from there, we have either package feeds or we then go into creating images. And this is the workflow in one picture. We'll dive into the details in a little bit, but first, are there any questions?
Hey Jan, so when you say we are source fetching here,
Yes.
from where we are fetching? I mean, it's
Okay,
from.
so by default, it would be the upstream source. For example, a Git repo or an upstream table. I'll get to that in a little bit once we look into how is that defined. There we will see how that works. But there could be also local mirrors that you can do. Yeah. So long answer short, we do fetch upstream sources as defined in the recipes.
All right, all right. And
Yeah.
what is the patch application?
Well, you might need a patch to fix a build issue, which is kind of the usual case, or you need a patch for a security issue, right? So you have a stable version, but you need a patch for an issue, for working around a build problem and so on, right? So there could be there could be a patch that's kind of specific to the cross compilation of architecture, let's say RISC-V. Yeah, just to
So
make
can we say that whatever we are fetching from the source, that could be a batch also? I mean, could be anything. Okay,
could be.
thanks.
We'll get to that. Yeah.
Thanks.
Okay. Then let's take a closer look at Bitbake. Now, Bitbake is the central tool that executes all and everything here. So we will learn about the metadata. We call those recipes, right? It's we bake, well, not cakes, but images, right? But it's always kind of the same. And this is not just common to Bitbake. It's also done for other distributions. Debian, Ubuntu, Red Hat, whatnot, doesn't matter. In some way, they all define a list of ingredients and a list of instructions how basically you need to get from source to binary, right? This is very common for any distro. Yeah. Essentially, we define the sources, we define what options are chosen, how to compile, and how to package up. So let's take a look at this. So first, we look at the metadata side, aka the recipes. Now, we have 4 main categories of metadata. One is the recipes, which end in .bb. Yeah. This is a single package, like libexec or libc or right, or your application, doesn't matter. It's a single package. Yeah. Then we have package groups. Those are just collections. So if you install the package group, you install all packages. We have classes. With classes, we can share common functionality and we can inherit classes in the recipes. So example, if 2 pieces of software have the same build procedure, right? We could make that a class. Yeah, and instead of maintaining it twice in the recipes, we can splice it out in a class and have those recipes inherit the class. Yeah. Under the covers, we basically pull in exactly those instructions, right? So you could also do a spaghetti recipe, right? If you parse it out. But for maintenance, for simpler maintenance, we basically put that into a class. And we have configuration files. In configuration files, we only have, we tend to only do variable settings, like version of our distro or the, yeah, basically variables are in here. Okay, so next. Then we have special files. I call them a little special. We have so-called append files. What are append files? They have the suffix bb append. bb append files are interesting because what happens here? We define additional metadata for a recipe, right? So we have a recipe foo.bb, and we have an append file foo.bb append somewhere else maybe. So we can amend recipes through the bb append files. So this is a quite powerful mechanism, and we will see later how we use that. Yeah. We also can do include files, and there are two directives. One is called include, and one is called require. Yeah. Include is kind of an optional include. If the file exists, include it. Require is a mandatory include. So if the file is not found, yell. Yeah. So whenever possible, you should use require. Yeah. Include as include does not fail when a file is not there. It's powerful, right? But I'll probably say that a few times. With great power comes great responsibility. Right? Okay. So OE core, I did the statistics for master, and we have meanwhile over 900 recipes, 25 package groups, which are also recipes essentially. We have 215 BB classes with common functionality, 75 conf files, 322 inks, and about 22 images. The core image is a naming convention, right? So it's essentially layer, which is core, and then dash image dash. So this is merely a naming convention. But here you can see that in here we have about 22 different images defined that we can produce. That ranges from terminal console only images up to graphical images. Yeah. Okay. So let's take a look into Bitbake. Bitbake is the task executor and the scheduler. If we just say Bitbake my recipe, for example, then the default is to execute the build task. And executing the build task means that we execute everything that build depends on as well, right? So basically, this is the catch-all. Yeah. And more or less all the tasks that are required are injected before build. Now, there are options that you can add. You can, for example, say -c clean. This will execute only the clean task. Yeah. Clean means remove the build directory. For example, if something goes wrong, you can clean up the build directory and start over again. -c clean all means not just clean up the build directory, but also clean up the fetched sources and basically everything, right? So this is a thorough scrub. And then you can basically refetch again from the defined sources. You can also get a list of tasks. Bitbake -c list tasks will show you all the tasks that are available for this recipe. Bitbake has a couple of implicit defaults. For example, by default, the highest version of a recipe is built. So you could have multiple versions of a recipe in your cookbook, right? In your layer, you could have multiple versions of the recipe. By default, Bitbake will, well, use the latest possible, so the highest version available. There are tweaks. As I said, you can basically tweak, well, most everything. So there is, for example, a setting for a preferred version. So you can adopt that, change that. Or you can specify you want to build a certain version of that package, and then you can append this dash version. Now this version needs to exist as a recipe, right? So this just shows how you can select a particular version. There is also the revision, but this is less important meanwhile. Or, yeah, you give it a full path to a recipe to build. Now, when you run your very first build, or when you run a really big build, there is a helpful flag, which is either -- continue or -K for like keep going, which means even if there's an error, Bitbake will just proceed with any other tasks that can be fulfilled. Usually what happens if there is an error, Bitbake will stop at the next possibility. Yeah. And with continue, it will process any task that is buildable even with this error. You will not get a final image, for example, but it will produce all the intermediates that it still can, even with an error that happened. That is very helpful if you have a big project and a long-running build. If you let it, for example, run overnight, you get as much done as possible, and then you can debug what happened. Bitbake is also a task scheduler, so it will schedule as much tasks in parallel as it can do. So it will, for example, if you have 8 CPU cores, it will do 8 tasks and run like 8 tasks in parallel, right? If you have a bigger CPU, it will run more, and so on. Now, if we run Bitbake recipe, it will parse it will look for recipe.bb. It will parse the recipe. It will look for the build task and what needs to be done before. All the steps from fetch to unpack, patch, configure, compile, package, and all that whole chain that needs to happen will be executed. And of course, recipes can depend on other recipes. So we get a long chain of tasks that need to be executed. So here is an example for the default set of tasks that you tend to see. we have the task do fetch. You see the do underscore in front, right? So this is the actual task Python name that runs, do fetch. If you do bitbake minus C, then it's just fetch or patch or configure without the do underscore, right? Just note that. Okay, so we have fetch, download the sources, or locate it. If it's already downloaded, we might have it in a local folder, for example. So locate the file or download. We have unpack, which means the archive needs to be extracted into the directory where we want to build, where we want to work. We do apply patches. If necessary, we do then configure the software with the options given in the recipes. We then compile the source code. We call the install routine, and then we package things up into packages. So that's the binary representation. There is another step, the do populate sysroot. So this is taking the artifacts and stage them in a sysroot if other packages require it. If you want to see the tasks available, then there is bitbake minus C list tasks, which shows you everything that can be done. A normal execution example for a hello recipe would then look like this. We did kind of simplify this illustration. There are more tasks at the top, but we limited it now to the hello app here. And you see fetch, unpack, patch. There is a task around licensing information. We have the compile, installation, package, sysroot, metadata for the package, and then there's the actual package format chosen, right? IPKG, and there is a QA step for the packaging, right? To rule out usual mistakes or errors that will bite us down the road. As you have seen, we do quite a few steps after things are compiled. Yeah. And there are pieces in this process that are kind of either binary output or build output in general, build artifacts, we could say. Now, there's an interesting feature of Bitbake that we will learn about now, and that is the state cache. As I told you, we do put all instructions into the recipes and have the classes and all of this. So this whole piece of metadata, if the piece of metadata is essentially unchanged, right? The binary result is essentially the same, right? So what we can do is, if we have a cache of the binary or build artifacts, right, we can short circuit and use the pre-built artifacts. This is essentially what the state cache does. It's a very smart mechanism. It essentially hashes all the inputs, and then we can kind of calculate a hash and look up if that hash is in those artifacts. Yeah, I'm simplifying it, but basically we can parse all the recipes and determine, hey, do we have a pre-built artifact of such and such hash? And then we can say, oh, yes, we have that. Then we can say, okay, perfect. Skip a couple of steps, right? And use the cached artifact. This saves you a lot of speed on rebuilds. So this is a crucial piece for the day-to-day development. And this can be done for a couple of steps in here, from the packaging, from the sysroot, which is the build artifacts that are reused then by subsequent or packages, and so on. So this is very useful and will speed up the whole process. So for example, if we do a bitbake hello before this, and we do a bitbake -c clean hello, what did we do? We basically cleaned up the working directory, right, of the build we did previously. Now, if we rebuild, then Bitbake will calculate those hashes and say, let's check our cache, the state cache, if we have the results already, and if we find these, we can use them. So you see, instead of running the fetch and all of this, we just do the corresponding set scene tasks. So those come then out of the artifact cache, essentially. Saves us a lot of time. Okay, let's take a look at the recipes, because this will then explain a few more things that are going on. Okay, so what do we need? Well, a recipe, as for baking cake, we need ingredients. Yeah. So, for example, we need either to clone a Git repository, we need to fetch a release tarball. This is part, for example, of the source URI. Yeah. So those are either online resources, tarballs fetched over HTTP, local files as well. We'll see what this can be. Then to build this software, we might have dependencies. Yeah. And there are two sets. And there's a difference. So we have, on one hand, we have build time dependencies. Yeah. So these dependencies are required at build time on the build host to actually configure, compile, right? Do anything we need. Those are in depends. What could this be? Well, compiler, some parsers, helper scripts, whatnot, right? You name it. So build time dependencies versus runtime dependencies. So dependencies that are required when running on the final target. Yeah. So those two sides exist here. Build time dependencies in depends and runtime dependencies then when it's live on the target. Depends we need to take care of because we need to say how the software is built, right? To some extent, runtime dependencies are detected because we can parse the resulting binary, find out what libraries it links to, and so on. So we can, let's say, 95% of the time, or not, yeah, 95% of the time, our depends is taken care of. We need to just amend it in certain cases. For example, if there is a script somewhere and we need to make sure there's a like a bash present or whatnot. So in certain cases, we need to amend this. Usually 95% of the time, this is filled in for us. Once we have the build time dependencies, well, the next step would be to configure and compile. There are two main options here. There are variables that we can modify, usually amend. That will be used by the default configuration classes. So there is, for example, extra OE conf and extra OE make. So those are options that are appended to the configure call or to the make call. So we can influence that. We do not have to rewrite the entire command line. We just have to follow the default procedures from the classes and just do the little one or two tweaks that are necessary. So now we have basically things downloaded. We have all the helpers that we need to build it. We have configured, we have compiled it. In the end, we need to split things up into packages. Well, by default, it would be one big package, but think of it, you have a complex application library, whatever, pick your poison. There you might want to split things into different files and sub-packages. That happens with a variable called files. We will see that later on. Okay. Now let's look at a real recipe because that makes things a little more clearer. So this is, for example, the recipe ETH tool. This is like for illustration, it's probably not the exact version that you find in the repo right now. But as a start, what does it show? Well, we have this top section here with a summary, description, a home page. There is also a field bug tracker. We have a mandatory field called license. So this is a mandatory field. Summary, description are mandatory as well. But very important to us is license. There is a list of license names that you find in the meta subfolder in OE core, and you should use the same writing of the license files so we can identify the string. There is another thing regarding licenses, and that is lic files checksum, license files checksum. Let me explain that a little bit. The license here is what we declare, right? So you looked up the license file, which happens to be in the file copying, right? Which is extracted from this tarball over here. Yeah, so this is a file in this tarball. We add here an MD5 sum of this file. Why do we do this effort, right? Because essentially you need to find the file in here, you need to get the MD5 sum and so on and so on. Well, think of it. At some point, the license changes, right? And we want to know if that happens. And then the checksum will not match and we will notice. So those are important here. Here's also an example. If the license is part of a certain source file, then you can even specify the start and the end of the license. And then the MD5 sum is basically the hash between those two lines. Okay. Let's talk about source URI. So source URI is a list of URIs. So a URIs is either, well, let's look up what this kernel org mirror is. Kernel org mirror is a variable, and that variable is defined in one of the core config files. And I'll just paste it over here so you see it. This is an image. I'll paste it down here. I'll make a mess here. Anyway, okay. So kernel org mirror is an HTTPS link. Okay. So a source URI can be either HTTPS, it can be a Git repo, it can be SVN, it can be a file. Now, this file means relative to a certain path, and there is a built-in set of rules where to look this up. So those tend to be next to where this recipe actually is. Yeah, we'll look into the details then as well. Okay, so it's either files next to the recipe, it can be an online resource, so some source where we find the software we are looking for. Also, if we download a tarball, well, we want to know that the tarball is exactly what we expect. A breach into the server is just one thing that we want to catch with this, but we want to say, yes, this is the tarball that the maintainer, author of the recipe intended here. Yeah. That's why we have two checksums. One is the MD5 sum of this ETH tool tarball. and the SHA-256 sum as well. Now, I already used one variable here, kernel org mirror, right? So this is a variable defined elsewhere that's replaced here once we parse it. Over here, you also see another variable, PV. What is that? Well, this is interesting because PV is a shorthand for package version. And package version is a variable that is automatically populated more like essentially from the file name. So there is a definition. We have in this recipe here, the file name is ethtool underscore 3.15.bb. Yeah. And the first half here, ethtool, well, this is the package name, right? And the second half is the version or the package version. So guess what? PV is replaced with the 3.15. And PN over here, this is the package name. So down here, PN will be replaced with eth2. That gives us quite some interesting options. An update from 3.15 to 3.16, well, is kind of easy, right? You just move the recipe from ethtool 3.15.bb to ethtool 3.16.bb. Yes, you probably have to change these two checksums then, right? But the rest should be the same. This is quite helpful in a way, and as you see here, a lot happens over conventions and defaults. And that saves us a lot of time because this is a full recipe. Wait, where are the instructions, right? We just provided the sources. Well, look down here. There is an inherit statement. And this inherit statement says, yes, this is a package which is based on the AutoTools mechanism. So configure, make install. So with that and the default options, which we don't need to modify in this case, we have everything in place. The ptest class is a class which gives us a way to define a package, a sub-package with a test suite. So if this ethtool package has a tests subfolder and has all the necessary hooks, and we inherit ptest, we get a ptest sub-package. So pn ptest. So ethtool ptest sub-package, which is populated with the test suite of this thing. But in this case, what we cannot auto-detect is the need for the make tool to be present at runtime to execute the test suite. And here you see the use of the runtime dependencies for the PNP test package, and there we add make. I'll explain the different ways to add things. For now, we just take that as granted. Okay, so this is a full recipe. Yeah. Let's say beside the boilerplate at the top, you actually only have to specify the source URI to checksums and basically inherit the class, right? So it's not hard. We have a lot of functionality already there at your hand. So what do we do in a recipe? Well, we take inputs, source code, we take tools, compilers, utilities. We can produce bootloaders, kernels, libraries, and so on. So everything we need can be done in a recipe. We also have package group recipes. They are not much different. It's just they have no sources, right? They only have they are kind of empty and just have runtime dependencies to pull in more stuff. And in the end, we have a special category recipes for full images, essentially. Those are little different because they have no configuration, no compilation, right? They just assemble what has been built previously. Okay, now to write recipes, we need to know a few things about operators that are used in recipes. The most important one, well, we have the assignments here. So you saw here, summary, note the space, right? Underscore, space equals space. Those are all assignments. Now we differ. We differ assignments by a so-called late assignment. Late means it is assigned kind of at the end of the parsing. Yeah. We have a default value with the question mark. We have also a late default assignment, and we have an immediate assignment. So the immediate assignment means if there is a variable like kernel org mirror, we do expand this right away. Yeah. I'll come to that in a bit. Then we have different ways how to append and prepend. We have the append with the dot equal. That's an append at the end. And we have an equal dot. That's a prepend. We have an append with space. That's the usual plus equals. And we have a prepend with space. That's the equals plus. Let's go back here. Here we have the plus equals, you see? So this is an append with space. Now, why do we have two types, with and without space? Well, the reason is there are variables that are space separated, right? And there are variables that are not space separated. Let's say have a a comma or a colon in between. Yeah, and that's why we need to differ between without space and with space. Okay, it depends on what you are modifying. There are also the append operator, which is basically a nicer way to do the dot equals. So this is kind of the preferred way, meanwhile, because it's more clear and not, you can easily overlook the little dot here, right? So there is a:append and a::prepend, which append and prepend. And there is a remove operator, which will remove something from the variable. I'll say that right away. Use that with care, because there is no way to undo the remove, essentially. This should be kind of the very last resort, if you have no other way. And in principle, you leave that hammer for the user and don't do that if you don't have to. Overrides. Okay, so there is a so-called override mechanism. And for that, we have a variable called overrides, which is a colon delimited list. And let's say we have variable a, which has lowercase abc in it. Yeah. And let's say the parsing then runs from top to bottom. So what happens? So we have overrides OS. So this is here in this list, right? So we will replace A because OS is in the overrides. Yeah. So this is a way, for example, to redefine variables for a certain machine or architecture, right? So this is a way to have a default value, but then modify things on the fly for certain machines. The same works with append and a modifier. So you can make a conditional append out of this. Yeah. Or a conditional prepend. So this is very common, especially like for adding things for a certain machine or for a certain setting. So this is a quite powerful mechanism that's used in the recipes. We can also unset variables, but therefore we have to really call them out, right? Unset date or unset do fetch no exec. So this is a flag, a task attribute. That's also possible. Okay. Now, there are default variables that are automatically defined or defined at parse time by the Bitbake tool or the policies. By Bitbake, we have the top tier, which is the top level project tier, the build directory. We have a variable layer tier, which is defined once we parse the different layers. And there is a file variable, which is defined whenever we parse a recipe. Yeah. Then we have variables for the build arch. This is the machine architecture that is executing the build. So this is your host machine. Important, this is not, yeah. And there is the target architecture. This is your target, for example, ARM or RISC-V, right? So this is the target architecture. Why do we need these two? Well, there can be things that we need to build that should run on the host, right? Helpers, the compiler, for example, right? So this needs to run on your host on the build machine. And there are things that need to finally run on the target. So that's why we have two. Then, as I already said, we have build time metadata. The first two we already talked about. One is PN, the package name. This is created out of the recipe file name. So to get a PN of my recipe, well, we need to have a my recipe my recipe underscore 1.0.bb. Yeah. For the PV, yep, the package version. This is taken from the end here. Let me add a little color. So we make that orange. This is orange. And the my recipe, let's pick whatever, a fancy color. Okay. So you see where this is taken from. The PR was used, well, some time ago. Meanwhile, this is auto-generated, and we, in principle, we should not mess from it, right? So I'll write up. Okay, then we have a couple of shorthands. We have P, which is PN-PV, PN-PV. So this is package name dash version. So my recipe minus 1.0. This is useful because a lot of tarballs, they package with exactly this scheme. So if you download a tarball for my recipe 1.0, then inside of that tarball, which is kind of sort of a universal convention, then inside of this file, there is a pn-pv subfolder once extracted. Okay, helpful shorthand. PF is the same with the PR, but as I said, PR is meanwhile auto-generated, so this is of less use meanwhile. There is file dir name in case you need the directory where this file is. And there is an interesting variable files path. Okay, so let's think of it. Bitbake just parses this recipe, right? Okay, file dir name is the directory where this recipe resides, right? So it's the directory where this recipe is. And then we have a variable which is called files path. And this is a colon separated list with the current directory, right? PF, PPN, or files as subfolder, or this directory. So files path is where Bitbake will look for files if we specify files in the source URI. Remember, I said we have a certain scheme where we look for those files. And here is it. So what we can do, what's the usual, what usually is done if you have, let's say, a script run ptest and or a patch and so on. Where are these? Usually they are in a files subfolder. Yeah. They could be in a subfolder with the package name as well. So to give you a live example, let's take a look. Where is the address bar? Let's go here. Let's go to Poky. Let's take a look at the scarf gap LTS and meta. Let's see if we can find ETH tool. Maybe here. Oh yeah, good guess. Here's ETH tool. Here's the recipe. Looks a little different meanwhile, but that doesn't matter. We have run ptest and a patch. So let's take a look. In here, it's a subfolder ETH tool where those two files are. So if we look at this rule set here, we will pick up files specified as source URI according to this. So first we will look in PF, then we will look in the subfolder P, we will look into the subfolder PN, it, right? That's where we find those files. And then we have two fallbacks. We have subfolder files, and this basically means next to the recipe. So this is how we locate the additional files, scripts, patches that we host next to the recipes. There is more build time metadata that we need to look at. One important is the top tier. This is the top level of your build directory. And from there, everything is a subfolder of. So we have one central directory, the temp tier. Temp tier is essentially where all the work happens. Everything is under temp tier. We have a work tier for each package. So this is where the work is done for each package. And here we have also the revision. And then we have a directory for the sources. We have a directory for the actual build. And we have a directory for the installation procedure, basically once everything is built and the the make install step essentially wants to write the output into a target directory, then this is the D for destination. So this is all the folders that are interesting for a given package, for a given recipe. The images are then written into deploy dir image. There are more subfolders in this deploy dir for the RPMs, for the basically packaged up files, and for other artifacts from the build. But the actual output file, something that you can write out to your SD card, those are in deploy dir/images. So this is, if we basically replace all of this, this is temp deploy images, right? I already mentioned the depends as build time variable, right? Depends is the dependencies at build time for this given package. We also have a variable called provides, which we set at build time, and those are automatically filled with the package name, essentially, or basically P, PF, and PN. And then we have variables that are important at runtime, because they define, for example, the runtime dependencies, aka if you install package foo, you also have to install package lib bar. Yeah, that's the runtime dependency, and that needs to be added, if not automatically detected. There is a weak runtime recommends. So those are recommended packages. And as you can guess, there is a setting to say, do not install recommended packages, right? So it's less often used. There are a few, but same with suggest, yeah. We have also more advanced and complicated options like runtime provides. We can, for example, say it provides something special at runtime and do very interesting pieces here, but or we can define runtime conflicts, which basically means you have foo and bar, and both provide could, for example, provide the same thing functionally, and we could say they conflict. So you can only install one of the two. We can also define replaces if, for example, a package changes names, but this is kind of advanced stuff. What we, as takeaway, we define depends at runtime, provides defines what the package provides at runtime. This is usually good enough as is. Our depends are auto-detected at the package step for us. We only have to add things which fall through the cracks and are not auto-detected. Yeah, the rest is kind of optional. Takeaway, depends and R depends where necessary. Also common is kind of the boilerplate at the top: summary, description, homepage, bug tracker. No, not optional, license and license file checksum. Those are important and required. They have to be specified. We have the source URI, as I already said, and we have files which, again, they are pre-filled with sane defaults, so things work out of the box. We only tend to modify these if we want to split things differently. Yeah. You have seen, if I go back to our ETH tool recipe, where is it? Here, we didn't have to specify files, right? So again, we have good, well-known defaults in here, and they tend to pick up if there's nothing fancy, they will pick things up on the fly automatically. That's why we didn't have to specify them here. So that's only needed in special cases if you want to overroll or split things into a lot of sub-packages. Let's take a look at another recipe so we see things in real code. So we have a recipe called BC. Yeah, that's some kind of a calculator on the command line. So let's take a look. This is the path. I looked it up. So this is the version in ScarfGap. Again, we have the boilerplate at the top: summary, homepage, description. We have the license file checksums. We have a depends statement. Let me add a note. We should probably add to the variable, right? And then we have the source URI. We have patches that we pick up. We have a ptest script. So this is also, the name is convention. And we have the MD5 and chart 256 sum for the tarball. So this is fetching a tarball. And then likely GNU mirror is again a HTTPS. Yep. GNU mirror is HTTPS FTP GNU.org. So this is again an HTTP something, right? HTTPS something, right? So this is an HTTPS resource. That's fetched. Okay. So let's look at this depends again, because this is special. We depend on the parser Flex. So Flex is a language parser, macro language parser essentially. And yeah, wait, this probably needs to run during configuration phase, right? So this is not running at runtime. This is actually running at build time and be either libraries that we need to link to, so those are target, but it could parser, the flex parser, but this is a native library. Can you hear me?
Yes.
Okay, I got a message of kind of your internet is unstable. All right. So this dash native is important here. I'll mark it because it says this is a package which is compiled to run on your build host. This dash native is the marker here. Okay, and then the rest of the recipe is essentially we inherit a class and this and that, and then we can build it already. And exactly that is what happens. We, beside the sources and a few variables, we then depend on classes which give us the common functionality that define the actual build steps, right? We do not want to reinvent wheels over and over again, because to be honest, most of that has been done millions of times already or follows certain patterns, and we can basically rely and automate all of that. So for example, in the recipe above, underneath, there is a statement inherit autotools, right? So there will be an autotools.bb class that we find in a classes subdirectory. Yeah. So we looked these up. We know what to do, and then the build can happen. Okay, let's see that in action. So we look at a different recipe called FLAC. So FLAC is an audio codec, and we have actually two classes here. It says it inherits from both AutoTools, that's the usual configure, make, install procedure, and getText. So getText is for localization, so for language support. So we actually to modify the whole event chain to follow the AutoTools mechanism, plus also inject what's required for getText. Now, this might mean getText, there might be another, let's say, parser involved. So guess what happens, right? We also add, as part of this inherit statement, we can also add dependencies. Okay, so we have a couple of extra settings, and then in the end, we do split things up. Let's look at this over here. Okay, boilerplate at the top, license, and then we have depends, and we have the source URI. Okay, so this defines where to fetch the sources. All right, next page. There are, meanwhile, variables, for example, for CVE, product names as well. So there is even more than we cover here. So I just want to highlight this. Okay, the important pieces for this recipe that we want to look at are these two. So we inherit two classes, AutoTools and getText. So what happens here, we pass then the BB classes and bring that functionality in here. On top, we can add extra configuration options in this variable. So this is the variable for AutoTools. There is another one if you are using CMake. So just follow the path and the documentation. If you are, for example, using CMake, it is likewise. For now, let's stick with the AutoTools. Here we add our own options, right? So we have a certain set of options that Bitbake needs to add to AutoTools already, right? One is them, what host architecture, what target architecture, where to find the compiler, and all kind of a very long command line that's injected, and then our own extra configuration on top. Well, here we say we want to disable this as a helper. We need to define where to find the libraries for the awk. You saw here that we depend on libawk. So at build time, we need libawk compiled for the target available. Well, and they need to be somewhere, right? And this is the place to look at. Same for the include files. So we need to help the configure script in this case a little bit, right? It cannot estimate our staging path that easily. Well, okay. So that's our local modifications. And then here's an interesting part. We add more configuration options, but what happens here? Well, this is kind of an embedded Python script. So this runs BB utils contains. So only if tune features contains Altivec, we will say enable Altivec. Okay, so only if we have a CPU which sets tune features to Altivec, we say use this optimization. So these are optimizations tailored to the actual chip, right? The other two are for Intel Core 2 and Core i7 tunes. So we evaluate a certain variable for optimizations and then add those flags. Yeah, so you see we can amend it, we can conditionally amend it in different ways. Good. Then the last piece here, let me change, make that a little smaller. The last piece here is that we define how to package up the different files and libraries. If we would not do this, basically there is a default set that globs for kind of bindir and libdir. So we would throw everything into the main package. Yeah. But here we say, okay, the main package is only the binary. Yeah. And then we create sub-packages for the different C, C++, or libok flag libraries. Yeah. So what happens is packages, you see this is, what is equals plus again? Equals plus is a prepend with space. So it's a prepend. Okay, so the order is important here. Let's see here. So we prepend. So, and then once we package stuff up, we go through this order and we start with lib flag. Okay, so this one is already handled. Then this one is handled, this one is handled, this one is handled. And then only the binary is left, right? So the order of this packages variable is important. Now, sometimes there are multiple packages built out of kind of a common source tree. And they share a lot of common metadata, between the two. In that case, what we can do is we can create an inc file. The extension here is important, .inc. Usually we tend to call then require, require some file.inc. So this helps in cases where we, for example, do sub-packages. We'll show that in this example. This example is about the conman recipe. And here conman has a main recipe, but also an inc file with common metadata between recipes conman, but there is also a conman GNOME, kind of a GUI build, right? Which might be the same source tree or a different source tree, but they share a lot of settings, right? If I build conman, I need to build a matching conman GNOME, right? So there are common settings, and those we put into the inc file. There is also a mechanism called package config. Package config is a mechanism that allows us to define configuration switches, and then have a central variable package config that we can modify and then enable things as we need them. Remember, we can modify a lot of knobs, right? And great power and so on. So let's take a look at this recipe. What we see here is at the very first thing, we require conman.inc. Well, let's take a look at the conman.inc. Okay, so here's the summary and the license file and the inherits and common settings even. And I'll come to this one in a little bit. But we have two recipes, conman and conman GNOME, the GUI client, right? So they then need to match in their configuration, and that's what happens here. So we have a lot of the boilerplate in that conmen.inc, and then we just define what's left. In this case, the source URI, and we here see also a recommend setting. So this is a configuration that's kind of recommended to install one, but it's not a hard requirement. It can be omitted. There's also a conflict. For example, there is another network manager package and you cannot install both, right? So there is only one process handling the network at a time, or they will fight for control over the network interface. Okay, so here's the inc file again. We already looked at this. We have here a lot of inherits. So auto tools we already know. This is the auto tool mechanism: configure, make, install. There we have also package config. Package config is another mechanism which helps detect libraries and headers. So that's another class. Systemd is for systemd support. Update rc.t is sys5 init style support, and update alternatives is used to provide alternative implementations or alternative configurations for runtime. Okay, then we have build time dependencies. In this case, those are target libraries compiled for the target that need to be present. So we need to link to dbus, glib, and ppp. So these need to be present at build time. And now let's look at this. This is also part of the inc file. And here we say something interesting. We have here a long list. I'll start here in the middle. So down here. So we look at this first. I think I can increase the size a bit. Yeah. Let me increase the size as far as we can. Yeah, like this. So we start here in the middle. We have a variable package config, and we have flags, different flags here, or modifiers, right? And each of that is a setting or enables certain settings. The syntax here is if this package config is enabled, do this. If it's disabled, to this. And then we have build time dependencies and runtime dependencies, and a few more. You can look up the package config scheme in the documentation, but that's the gist of it. So if enabled, if disabled, build time, runtime dependencies. So how would we enable, for example, systemd? Well, it needs to be part of this package config variable here at the top. And you see this is done in the recipe with a double question mark. So this is a late default. So essentially, it's there as a default, but the user can override it. User distro config, but in principle, we could override it. So in our own distro, we could say package config, could be in a BB append to conman, package config equals. Okay, so I need systemd support, I need Wi-Fi, I need BlueZ, and so on. So you see, okay, we can influence that. And for example, these three will switch on this part over here, enable Wi-Fi, enable Bluetooth, and so on. If we look at the default, there is Python expansion in here. bbutils filter means if 3G is present, then set 3G. If systemd is present, set systemd. So if in our distro features, which is basically our central variable for our distribution, enabling certain features. So for example, if we want to use systemd, well, guess what? There will be systemd in distro features. So this is a core variable. Okay, if there is systemd in here, then set package config contains systemd. Okay. If we enable Bluetooth, we set BlueZ. Okay, BlueZ. Yeah. So in the end, this then might look like, I'll make an example over here. Whisper, IP tables, client, systemd, BlueZ, Wi-Fi. We didn't modify the default, so it's WPA-supplicant. Okay. Okay, and now this is the end result. And each of these throws one section down here and adds this to the configure, to the depends and the rdepends and so on. Don't worry, you will grok that. You just need to get used to it and read a couple of recipes. It's not rocket science. Okay, so after that, this influences the configuration, the dependencies, and the runtime dependencies. Then the build runs, and we have here also support for the startup systems that exist. So either systemv scripts or systemd services. So this recipe can be compiled for both, right? Oh, well, for either init scripts or systemd. And at the top, this is the definitions for the init scripts. Down here is the definitions for systemd. Whatever is enabled, right, at the higher level, at the distro level. And this also bubbles down into a change that we need to do in the install step. Remember, there is the configure, there's the compilation, and then there's an installation step, right? And in this case, we do something to the install task. Yeah, do _install. append. So at the end of whatever is passed out for the installation procedure, we append a few things. And that's what we do over here. So for example, only if we are doing sysv init boot up scripts, then install the scripts. Okay. So this is essentially a shell with the Python executions wrapped in here. Then install the sys5 init script. Otherwise, if we are using systemd, this will be ignored. Yeah. The systemd service definitions up here do already a lot. So there is no section specifically to this because everything is already installed by default in the right place. But there is one thing, there is another config file that needs to be moved or linked or whatever in case of systemd. So that is this down here. And then we basically clean up a few things or move a file to this or that. So this is kind of cosmetics cleanup, whatnot. That happens here as well. Okay. I'll make a short pause here. First questions, and I think we'll do a short 5-minute pause in case someone needs a quick break. But first questions so far. All right. Okay. So next we will do a quick intro into, well, what can we do if things go wrong? How can we kind of debug the first things? Okay, so each recipe, once it's parsed, has essentially its own environment with all the variables, all the methods, the classes, BB classes that build this recipe, right? So in principle, we have an environment with all those variables defined, expanded, and essentially we can see what this S equals workdir or PV, PN, and whatnot, what all of this is, okay? So how do we get that? So to view the environment of the recipe, Bitbake can parse this out for you. Yeah, Bitbake minus E, my recipe. I tend to do that like with a redirection and basically pipe that in a file for later inspection because it's big, right? So that's just a hint from my side. I write it into a text file and then use my favorite editor to read it. Let me make an example because that's the best we can do. Wrong machine. Let me cheat. Okay. Okay. Source. Wait. Okay. There's my project, and now I say bitbake minus E. I just pick a random package, let's say BC, yeah? Then something happens. Bitbake parses everything he has to do, X, Y, Z. So after this finishes, we will see the environment. Okay, now what we can do is we can have Bitbake parse out the environment for your recipe or for whatever recipe you are interested in. We can grab for statements. So that is the variable S, yeah, a line that starts with S, and so on. So this is the source code for the recipe. Then what is the output of the the file? Well, the file where the recipe resides is in here, is in file. So this gives us all the information and the view of the parsed environment. Note beside bitbake minus E, there is a wrapper that is a little more convenient if you just are interested in a single variable. There is bitbake-getvar. So this is a wrapper script. It takes the recipe and the variable. Yeah. The recipe is optional because you could also have a global environment. Yeah, so I'll make that an option. But this is a helper, and in principle, this is very similar to this, just without the grep. Yeah, so it saves you typing if you use bitbake-getvar. Okay, meanwhile, here's the bc.env, and let me just search a variable, for example, s, and as you see, this is the definition of the source directory S. And you see also how it is set up, where it is set up, and how it's expanded, and the end result, the pre-expansion and the end result. There might be variables that have multiple sets or appends and so on. So the chain of events can be more complex than this example. But I wanted to show you the environment as is. So you can basically inspect everything. So if things goes wrong, take a look at the environment, and that will tell you exactly what happens. You can inspect individual variables. You can inspect where the build happens. You can inspect what's the output packages. How is this variable expanded? In what order? Maybe you did append or not prepend, right? And if you are just interested in one variable, then bitbake-getvar is a very nice shorthand. Okay, if things go wrong, well, where is the logs? Every build action or every action that bitbake takes is recorded in the so-called cooker log. This is in the temp directory, temp log cooker machine, and then the date. So you can find out the chain of events in here. Okay. On top of that, each recipe has a directory called temp with underneath the work directory temp. Oops. And this is, you can find it. It's the variable t, and once it's expanded, it's in the temp folder, work, architecture, package name, pf, temp. And in there are log files, right? Logs for each task and run files for each task. So in work.dir temp, there are log.do task name. Yeah. So they record the output of the tasks, and there are run do task name files. Those essentially record the scripting or the script that is run for this task. So you can actually inspect, well, the output in the log, but also exactly what's executed in those run files. You could also, wink, wink, jump into the execution environment, and this is the so-called dev shell. You can look this up in the documentation, and then you can actually execute these run do something scripts. Yeah, so you can actually tell Bitbake, bring me into the exact environment, and then you could actually run these and debug it within the build environment. Yeah. So look up the dev shell in the documentation for that. Okay, so this was now a lot of drinking from the fire hose. Now give me the procedure how to get from basically downloading Poky to an image. Okay, I can do that in one slide. We clone, in our case, let's say the scarf gap branch of Poky, right? Command line number 1. Number 2, we do a build with the default settings, the default reference distribution and its settings. Check. So we source the OE init build env script, and my build is the subfolder that we do the build in. We could modify a file called local.conf. Actually, it's in the subfolder conf, local.conf. Yeah, and then it doesn't fit anymore. We could make some modifications, but that's not kind of not doing anything special. And then we would call bitbake to start the build. With or without -k, this is just to make it proceed in case of an error. So this is actually optional. Okay, so download, source the build environment, and then call bitbake. Step 2. Step 3, if it's x86, for example, or QEMU x86 as machine, which is the default. If you do not change anything the default is QEMU x86, so an emulator target, which is very convenient because, well, we can run it under an emulator. If we did not change anything, we can just call a helper, and that helper is called run QEMU. And run QEMU will start a virtual machine on your host and start the build image. I think this is even optional meanwhile, right? So step number 3, yeah, run in the emulator. There are a few options that I would recommend for simplicity. Slurp is user mode networking, so you don't need to provide sudo while starting this up. So that would be recommended. KVM for speed. So those are 2 recommended options to add. Yeah, and then last step, profit. Well, okay, there is likely more. Yeah, you will want to modify X, Y, Z, and do this and that. Okay, but that's now your part. Let's take a look at how things look like on your host system. So let's say we are working in your home directory under a folder called Yocto. Change that to your liking, but underneath of that, there will be somewhere a Poky, a folder with Poky with everything in it. And no, you are not supposed to make any modifications in there. Yeah. David will later on tell you how to set up layers, and there you can make any changes that are required. So never touch that unless you are doing an update of Poky itself. Yeah, there will possibly be your build directory, or as in the previous slide, your my build directory. And maybe there's a folder for downloads and there's a folder for the shared state cache. Remember, like from the beginning, the artifact cache. Okay. Okay. In the Poky subfolder, there is Bitbake included. There are scripts included. There is this magic OE init build-env setup script that we need to run. And there is a set of metadata that's in here. Okay. There are a few more files meanwhile, but for simplicity, we trimmed it down to the most important ones. Okay, so setting up a build directory. Well, you saw me doing that before. So I go into my top level folder, then I have to source OE init build-env and give it a name, either build, my build. That's up to you. Note, whenever you start a new shell environment, right? Whenever you start a new terminal, whenever you reboot your machine and so on, you need to enter the build environment again, right? So this OE init build-env, you need to run it again. Make sure that everything is set up for the build system to run. Now, your build directory will then contain a couple of folders. The most important ones are listed here. We have some cache files, we have a log files, but for you, the most important ones are essentially 2. bblayers.conf, which contains a list of layers to use. So Bitbake, when you call Bitbake, kind of the first thing it looks at is BB layers, right? What's included. And the second step is, beside everything, what's the local configuration. Yeah. So local.conf is your place to define, like, what machine am I building for, right? So this is your configuration where you define your choices. There's an optional site.conf. Site.conf is interesting for settings that are common for you. Let me name two. For example, your downloads directory or the variable DLDir, or your state cache, state_dir. So this is very useful if you want to reuse already downloaded files and so on. I tend to stick such settings, right? Download folder, artifact cache, state cache, into a site.conf, right? And then reuse this across builds of mine. So this is very useful. It's optional. It is read in if present. Okay, and then there's the folder temp where everything happens during the build. There might be temp dash something. Let's say glibc. So there might be other temp subfolders. This depends on the configuration. But all the work, all the artifacts are in here. So that's the most important folder in the end. What's interesting, if something goes wrong, well, what you can always do at the expense of CPU time, blow away temp. Yeah. If you are unsure, and you can blow away temp. If you have download dir defined, state cache defined, then it's merely your CPU extracting archived files again. So it's then more extracting disk bound and not kind of a lot of CPU that's required then to recreate all of that, because with the cache, remember, we can recreate build results quite fast. Okay, building a Linux image. Here's the general procedure, kind of as a reminder. We have Poky downloaded. We source the OE_init build_env. We have an optional build or project directory name that we can specify. Maybe we do edits in local.conf. Maybe we specify a machine there. We could specify a downloads there and a shared state directory, or in brackets, do that in a site.conf that you can more easily reuse. Then you build your selected image, or image minimal, for example, and so on. Okay, so here's an example how to modify conf_local.conf in your build directory. Very common. Well, you might want to build for a different machine, right? So here, pick your poison. That the default is QEMU x86. You could pick QEMU ARM. You could pick the machine defined by your BSP. So that is one of the very common settings here. You could specify the download there. Now, the default, if you do not override this, is that it is below the build directory, which is top tier, right? And then it would be local to your project. Yeah. If you want to reuse it across multiple builds, you might to do this. I have this, for example, in a site.conf, and I have it like more or less like this as example: home, username, Yocto. So that would be the setting in my case, and I do that even in a site.conf. So that's up to you how you want to do that. I just give you an inspiration here how to do this. The machine here is not necessary. So this would be the setup that, the minimal setup that we would recommend. If you run Bitbake, it will build you an image of an entire bootable Linux distribution. Yeah, there are multiple images available as part of the OpenEmbedded core set of recipes. You find those in the Meta subfolder. And there is, for example, core image minimal. There is core image minimal dev. That means there are some development tools there. We can look at the recipes here: Meta, recipes, core, images. So there is the minimal image, minimal dev with some development tools. Then there is something for use with initramfs. Yeah, a p-test image with the test suite, so that's used during testing. So here are some examples. Now, how long does the build take? Well, the faster your computer, the faster it will be. In general, Yocto tries to be independent of your build host as much as possible. So it will bring and compile also the compiler and all the necessary tools that run on your host machine. So we only take little from your host as less host dependencies as possible. Why? Well, if we want to be reproducible, we cannot depend on the host binaries and libraries, right? So we basically bring all batteries that we need and set those up and compile them. Usually it's done from scratch in a few hours. Yeah, and the next time you build, remember there is the download cache and there's the state cache. It will be faster because if you did not change a lot of variables and settings, or if it's the same configuration, essentially, it's merely extracting pre-built artifacts from the cache. And it's then just IO bound. So with a fast disk, it will be fast. Run QEMU. So here's the big picture on Run QEMU. It's a helper script that sets up the command line for the virtual machine. It's a wrapper. It auto detects a couple of settings. There are predefined command line snippets that we construct here. And by default, the most simple invocation would be just run QEMU. It would start a graphical window. So there is, for simple images that do not have graphics, there would be, for example, the no graphic option. I already said there is a KVM option. So if you are running an x86-based image, you can use the speed of the KVM accelerator. So this is faster than pure emulation. And there's also the SLIRP option to enable user space networking. So you don't need to give sudo for the networking setup. So there are a couple of options, and I think David will give you some more on that later on. All right. That was the first part, drinking from the fire hose. If you have any questions, then please go ahead. Otherwise, David, should we do a very small break?
Yes, I will start at the half hour. So let's go ahead and take a break until I guess 3:30 UTC. And by the way, the -K option is if you want to keep building, even if there's some errors, you can get as far as you can.
Yes. You mean top of the hour?
So the top of the hour is no, the break is actually till half past. So you're ending in 10 minutes early, so that's great. So we'll do the full 40
Okay.
minutes break, and then we'll start at 3:30 UTC, which is 7:30 West Coast, where I am.
Okay, so we have 10 minutes for questions.
Yes.
All right.
There was a question about SS state, sharing it between people building different machines and such. Yeah, there's a very complex SHA for every entry into the SS state table that includes stuff like the machine and the configurations and the C flags you did and everything they can think of to make sure that any contribution to the S8 cache from any build will not collide with something similar. So you're very safe sharing SSA amongst very different, disparate builds.
Yeah, so there is even kind of the S state can be, for example, shared over NFS. You can have your builder populate an S state folder and or sync that to a server. There's a variable called S state mirror. You can look that up in the Yocto documentation. So there are means to share pre-built artifacts because if you are in a local fast network, right, and basically can download artifacts faster than you can build it, yep, that will be a pretty good speed improvement. And as David said, the mechanism makes sure that with all the settings, with all those variables taken into account, we pick the right artifacts.
Hey Jan, so this reminds me some other ideas. So can we make a kind of recipe for the cache itself? And while building some particular project, we can fetch that recipe first and put the cache to build the faster. Is it possible?
Well, this is the so-called S-state mirror. So you can set this state mirror variable globally, for example, in your local.conf, yeah, and have it point to, for example, a web server. And this web server essentially contains the state folder of your, let's say, nightly builder. Yeah. So for example, what I do, I have a nightly builder that builds my project. And it does two things. I do upload the download folder, yeah, to it, and I can use this as a mirror. And I can upload the state cache to that web server and use it as a state mirror.
So how much time you are saving with this mirror?
It depends how fast you can download it from that mirror, right? So
Oh,
the fastest setup would be to share downloads and state via NFS, for example, right? Local network, right? And then the next step up would be share it over an HTTP server. But note, well, for the HTTP server, we always have to fetch it in full or query if it's there in full and so on. So that's a little slower than the local setup. So it depends. If your machine is kind of a CPU monster with kind of very good internet access, then sometimes kind of rebuilding stuff is faster than downloading everything. It depends.
Correct. Got it. Got your point.
How do parallel builds work in Yocto? Does Yocto make use of Ninja by default? I'm not familiar with Ninja myself. Parallel builds, you're asking how they can have so many threads running at the same time. It's because the dependencies between the tasks, there's many tasks that can run that are independent of other recipes. And we'll actually show some of that at the end of this talk when I look at the build dependency tool. So like there's some unpack and fetch tasks that can run on many different packages at the same time so that they can all run in parallel. It's only when you hit a dependency on a previous recipe task do you have to wait and wait for that. What are the advantages of depends and are depends for package variable? Um, I'm not exactly sure about that question. We'll have to come back to you with that. If there's an expert who knows on that particular question, please let us know. How often are build?
If I may add to that, there was an example shown regarding the package config, and it was mentioned, okay, if we define a package config, it would interpret the depends and are depends from the package config where we define. But my question is that, so basically when you write a recipe, you could also define your depends and are depends on in the recipe. So how does it works with the package config? Why should we define it twice?
Yes, and I'm not sure the answer to that question.
Okay, cool.
So we'll have to ask someone else who knows more about that part of the thing. Okay, how often are vulnerability fixes released? The Yocto thing. We're doing updates all the time. There are major releases. We're doing minor releases at the beginning, like once per month. So you get 5.2.1, 5.2.2, 5.2.3. So in the beginning, there's like a once a month update. And yes, the major releases are every 6 months. And we're working very hard to keep all the CVs up to date. Is it possible to build Android OS using Poky layers? In theory, you could build anything with Bitbake. I'm not sure about just Poky. I know there's one for Ubuntu reference. We can look that up later. I'm not sure. 5, is it recommended to upgrade Poky from THUD to Scars Gap? So THUD seems pretty old. Let's, how old is that? Let's go Linux toaster releases. THUD. THUD, my goodness. 2028. Yes, it would be very advisable if only for the CVEs and the kernel updates. And you're trying to go to, I'm sorry, THUD to Scarscap. Scarscap is, yes, and it's a long-term release. Definitely jumping to a long-term release, a recent one, is very advisable. There'll be a big jump because that's 2 years, 6 years jump. So it'll take a little bit of time to make all the adjustments, but it's very advisable.
Cool, thank you.
Yeah. Okay, so I'll try to get back to you on those other two questions. I've got them captured here, and we'll try to get you some answers. Okay, let me reshare my screen. Share. Let's bring up the slides. Doesn't want to jump to my slides. There it is. Okay, do people see the slides? Layers. Okay, let us continue. Layers. We're going to talk about what layers are and how they are very crucial to how we get the job done in building and merging all of the content that's available in projects. And reopen chat. Okay. So here's the challenge we have. How do we assemble our products from all the different contributors, all the different independent sources, all the different variations of everything, and that we'd like to use as building blocks? How do we bring that all together? How do we organize our own content into easy to use logical units, and that we can override with updates, later revisions, and all that? And how do we manage both the short and long-term cycle of our development, the long-term life cycle of our content? And for some people who just jump in, this is not a problem. You just grab what they have and build something, and that's it. But for people who do long-term development, for example, I'm from, my name is David Reyna. I've been with the Yocto Project since 2013, there-ish, and work for Wind River Corporation. We've adopted the Yocto Project to replace our own build system with the Yocto Project and Bitbake a long time ago. So we're very dedicated and very much enjoy the Yocto Project community, having long-time contributors. And we have products to that point that had to be supported for 5, 10, 15 years because we sell to automotive, medical, and other companies. So long-term life cycle is very important to corporations, certainly the commercial partners, the Yocto Project, and to many people. So we have to take care of that, and layers is part of that solution. So what is a layer? It's really just a formatted directory. It's a metadata that's provided, and the metadata in general is provided in a series of layers that allow you to provide content, to overwrite content without changing someone else's content. That's very important. The layer is a large collection of metadata in the form of recipes. It's actually much, much more, but you start with recipes. It could be used to represent OE core, BSPs, applications, new code, overrides to classes, alternate tarballs, alternate Git repositories, anything you can put into a layer that can contribute or replace content. And layers do have a priority. You can order them, but you can also have priority that would override the ordering. So that makes sure that things are added in the proper order. So your newer content, higher priority content, content specified by your image recipe will take the proper precedence over previous content to make sure that you get what you expect and what you need. So layers, they're layered. literally. So at the bottom is the core content, OE core. On top of that, at least for Yocto Project, is the distribution, which is Poky. And then you have the BSP layers on that because they depend on the content from the layers below. On top of that, the UI, the GUI, Naughty that you're familiar with, all the other content. On top of that would be your layer, the commercial layers for if you're using or other middleware layers. And then your layer is at the top, you as a developer, so that your content is latest and greatest and has the highest priority by default. And this is how you assemble a project, a product, a project, and everything. So very abstract so far. Layers are ordered by inserting them in the BB layers file in your conf directory. And when you instantiate a build directory, you get 3 for free. You get the meta, which is the core layer, Meta Poky, and then Meta Yocto BSP, just as we mentioned in the previous slide, like here, Meta OE, Meta Poky, and then BSP. And by default, your current later project is the last one. BSPs are the layers for specific boards, specific hardware platforms. We can define machine configurations for those boards, BSPs. Those add machine-specific recipes and customizations. The primary customizations would be around the bootloader, how you're going to configure the kernel to support that particular board, any applicable graphic drivers, and any additional recipes that you need for that particular board. That would be in the BSP type layer. And if anyone has any questions, please just go ahead and unmute and ask your question directly. I try to watch chat, but limited bandwidth. So the primary principle of Yocto development is that pristine source with patches. You do not want to edit someone else's content. You do not want to edit OE Core or Yocto or BSP. And you do not need to. You can overwrite that content with your own layer so that you can provide what is important for you, for your board or your project or your business rules, whatever, without having to change what is below you. And that's very important. For example, when you change from one release of Yocto to the next, if you can leave those layers alone, then you do not have any patches that you have to carry forward, you have to rebase, you have to manage. That's very crucial in maintaining your life cycle for your products. So if you keep all your changes separate from the original content in the layers below you, that makes it much easier. And for the person trying to move from THUD to Scarscap, that's part of the thing. Hopefully you did not edit any of the source content so that you'd be just swapping one for one, and then you just have to make your changes depending on, of course, the changes in Bitbake syntax and whatever. So, but there's rules to help you with that. So use a new custom layer for your own modularity, maintainability. I mean, at Wood we use those all the time because we're also changing between customers and releases and rebasing, and that's really helps us get the job done. Layers also allow you to easily, exactly, port from one version of Yocto Pocket to the next version. And the if you want to see all the layers, we have a tool called the OpenEmbedded Layer Index. Has all the layers. And here it is. Layers.openembedded.org, that's a web server that's being sourced by OpenEmbedded, has the thing called Layer Index that tells you all about the layers and their recipes, the machines they wrap, the classes they wrap, and the distros they define per branch. So this is the core source of information about what is available in Yocto Project and OpenEmbedded that you can draw from. And with that, we're going to have a quick little fun exercise. I'm going to paste this, copy this link. Oh, let me just escape. Oops. Here we go. Sorry. Okay, I'm going to copy this link, paste it into the chat. I'd like you to just try, everyone, just try this out. See how far you can get. Open up in your browser and see if you can find the layer and our recipe that provides support for Raspberry Pi. And see if you can find the recipe and layer that would add the Apache server into your system. And you can look at the images and see, look up core image base and see what license it uses, for example. And as a fourth exercise, see how many tiny distros there are. So I'm going to give you a moment to try that out, and then we'll all do it together. And when you find all four answers, put it in the chat that you succeeded and found that information. Okay, Ivan is first out of the gate. Well done. Let's go back to the questions. Blues, that's an interesting answer. There are in fact many different layers and recipes that supply certain things. Apache 2. Well done, Sergey. Okay, has anyone found the core image base? Okay, very good. Shibram found an alternate layer that has Raspberry Pi support and is specifically tied to Barrett Bettle. Ivan again, very good. You got a, yes, MIT is the license for core image base. It is in fact, MIT is the license for all of Yocto Project. That's the core license that we use. So that's consistent. Okay, we have one more question we're looking for an answer for. How many tiny distros are there? Everything comes through. Okay, I'll give you just one more minute for each of you to try it also. Peter, Matt, very good. Okay, well done. So let's all try this together just to see how it is done. So we look for layers. We just look for a keyword, in this case, Raspberry Pi, and it pops right up, Meta Raspberry Pi. And as it pointed out, there are many variations that you can use that provide different levels of support, very different focuses, bare metal, Zen, resin, microservices. So these are all candidates for how you might want to base your development for Raspberry Pi by bringing in this repository. Let's go to the second set question, which is Apache. Let's try Apache here. Can't spell. Okay, now, oh, yep, here we go. Apache. I'm not the right place. Let's look at recipes. Apache. A-P-A-C. And okay, here we go. Apache 2. Any other alternatives? Not so much. I've always wondered why Apache 2 is the recipe for Apache server, but I guess there must have been Apache 1 or something. And yes, the layer that is found and defined in is a meta server. Let's just take a look at that. So it provides Apache WebSocket, Cockpit, a bunch of other recipes that are used to include. And once you include this recipe, you get access to all these recipes that you can use to enhance your product, to bring in different skills and features. Okay, let's go back. Okay, next question was core image base. Yes, you look in the distros. Sorry, image. This is images are recipes. So we can look here. And yes, this here we are. Got two variants. Let's look at this one. Yes, license is MIT. Console-based only image, version 1. The list of here's what inherits. Here's a recipe file. If you want to take a look at how it's defined. Very simple. It just inherits this class and it's done. So very much the core. There's the MIT license definition, summary definition. And they add a splash. So when you bring this up, you get a splash on the screen. It's one of the image features. Last question, tiny distros. So yes, we go to distros. We enter tiny. So Poky is not the only distribution that Yocto Project supports. There are many, and 1, 2, 3, 4, 5, 6, 7, 8 is the correct answer. And they're all in these different layers. So you can really tune your system by which layers you select. Okay, that was fun. Thank you very much for playing along. Okay, let's come back to the presentation. And let's go full screen. Very good. Okay, we can create layers manually. We can also use a tool called Bitbake layers. Typically, we name our layers with the prefix meta, just by convention, just so we can keep them separate from other content. So we'll show you how you create one. We'll just call it meta-ypp-dd. So there's a tool, as I mentioned, Bitbake layers. When you you can fetch stuff directly from the layer index that we just saw. We can show what layers are present in this particular build. We can show their overlays, show their recipes, show their appends, many things. We can add a layer to our local build project. In other words, it adds a layer to the bblayers.conf that we saw earlier, so that it's included when the Bitbake runs your build. You can move a layer from BB layers and such, flatten, many different features. So you can really see what is available and kind of manage your layers very easily from this tool. If you were to do this, this is how you do it. So see your project, source your build environment, and run bitbake/layers create. We'll call it, here's YPP. It should be meta YPP. That's a mistake here. Let me just go ahead and I'll fix that later. Let's pretend it was meta YPDD. Okay. And yep, here's where you fix it here. Okay, so when you do that command, it creates a default layer with a basic content. And the content required for this to be a layer directory is that you have a conf directory with the layer.conf in it. We'll look at that in a moment. We need to start with some kind of license, and the default is MIT, as I mentioned, for Yocto Project. We want to have a README so that we always start with something, a good practice, and it provides you with, I'm getting all these, here we go. Oh, stop that. I'm getting all these things here. Escape, no, that doesn't work. Stop that. Let's come back to the presentation. Here we go. Okay, full screen. Gives you a default recipe, which is example. It just has example recipe inside of it, just to kind of get you something to start with, just get the framework going. So normally you would go in and start with renaming content and adding your own content to this, otherwise default layer. Okay, if we look to a full size layer, this is what the meta looks like, the core base layer for everything. And as you can see, it's not just recipe directories. They've got classes, classes for global, classes for recipes, the conf, of course, which has layer.conf, a files directory, a lib directory, a site directory. So this is a much more complex and actualized layer. You could also have like a download directory. You could have one that holds your tarballs and your local Git repositories. You can have anything that logically brings all this content together. So this is a base layer that kind of covers all the different ways you can use Yocto Project. You probably, if you have a layer that's specifically for a BSP, of course, would have content that actualizes that BSP with all the variants and options and recipes and class overrides, all the content necessary to define that particular logical unit. You might have a layer that covers a particular release that you're producing that has the all the business rules, it has all the boards for that, it has all the layers, the specific versions, the supported content for that particular release, so that you can really capture what is specific to that release, and probably have a layer below it that is for your general releases for that general board line. So you can really divide it up and have as many layers to capture the right granularity of change so that it is easy to define a specific result and also make it easy to transition from this release to the next one and not have to rework all of your content. What is in the layers.conf? Let's take a look. First of all, we add to the BB path this layer directory so that it's included in the searches for recipes when Bitbake tries to resolve content. Where are we going to look for the BB files? In all the usual places inside recipe star.bb and BB append. What is the name of this collection? This particular layer is going to be called YPDD. What pattern do we use? What's its default priority? The priority is 6. I'm not going to tell you if the priorities are better, lower, or bigger, because if you need to do your priority, you should probably look that up to make sure you do exactly right all the different ways to define the priority and the consequences. And that's all defined in the Bitbake manual. What does it depend upon? Core. What is the compatible release? Styhead in this case. You can make a wider range of compatibility. This one, we want to make sure we tie it to a particular release, just as example, but you can make it tied to multiple releases if this layer is compatible with multiple releases. So this is kind of a quality check value. So you can make sure you're not trying to apply a layer for Rocky that does not work with Styhead. So these are all the regular ways you'll configure and apply a layer. The fact that these are all defined means they can also be changed. So there's been someone somewhere who had a change. They needed to put the recipes in a different location or the BB files in a different location or something else. So these are the general rules, but you can override these if your particular layer needs to be defined in a different way that works for your distribution. Again, these layers are defined and ordered in the BB layers file. When you ran the tool, it did it for you, put it at the end as a courtesy to you. Because if it's not in the bblayers.conf, then Bitbake cannot find it, and you will not be able to use those recipes. It'll just error out, say recipe not found, recipe not defined. So you do need it in the layer. So what is in the example.bb file, just to kind of get you out the door? It's a basic, very basic, bare bones recipe. It has a summary, description, a license. You kind of have those three. And instead of doing any builds, it does a little fun little trick. It just adds a task for Bitbake to just display this content via this Python routine, this Python fragment. And so when you do a build, this just prints out right before the do build normal task. So this shows you not only how you can add a printf into your layer, into your recipe, but also says how you can order it and include it into the ordering of the Bitbake actions tasks. So that's kind of fun. And we'll show that in a little bit. So you can build this, you build example, it finds example under that layer, because it found that layer under the BB layers. And yeah, that we just looked at. And in fact, let me just do that right now. Let me come in, let me open my session to the beginners class. Okay, let's ls. So let's source Poky rather OE. Okay, so I'm in the build directory. So we'll take a look around. I've already instantiated my meta thing. Let's do a tree on that. Okay, there's the example recipe down there. The example recipe core, that's part of the later part of this trading. But there's your recipe layer. Let's just cat it. Cat meta recipes, example. Let's cat that guy. Just like I promised, there's the content. So if you bitbake this, it's going to look for this recipe, look to the layers, find the layer for this meta YPP, YYPP, find the recipe example, and build it. And oh, I've built it before, so let me do one more trick. And you saw this trick in the steps before from Jan Simone's section. You can add a little command here. I'm going to clean this recipe out, so I'm going to build it from scratch because I want to see it actually build. So pretty quick. Now let's try to do the example. There it goes. And there's that message. So as promised, it built this recipe. It executed this Python little piece of code and finished. So yay for that. Okay, let's come back to the class. Images. We talk about images, the recipes that define them, and how we use that to build the system images that we're going to then send to our BSP people or run on QEMU or on our own. So building an image creates an entire Linux distribution from source. You got your compilers, your tools, and your libraries. You selected your BSP or wrote it yourself. You got the kernel. Now we just have to kind of start assembling the root file system with base OS, the services, the applications, all the content value add that you have created. So how does that work? There are some pre-created image recipes. You saw some, the base ones that we looked up earlier. But of course, you're going to want to make your own image recipe that's going to define exactly the content you want on your device. That's what's so great about Bitbake, Yocto Project. You can really granularly define exactly what goes into your target and manage it exactly. It's always preferable to existing image recipe and or inherit. So we often inherit from the base class and then start adding our content on top of that. Do we have a question? I hear David Hunter. David, if you go on mute, that'd be great. Thank you. Images. Oh, got a question. What directory is for a new board ring up? Let's come to that question a little bit later. So your question is, how do you define a BSP within an image? And we'll come to that. So, and you add your packages to the image with the image install variable. This is what one will look like. This is how you can create a image directory by yourself. You just, we'll do it inside the meta YPP DD layer that we instantiated a little bit ago. You create a recipes-core directory, and then you create a subdirectory called images, and that is how Bitbake can find this image definition. So you put a BB file, inside that images, and here's the content you would add. So description, what is this image for? The license, default is MIT, core image files, image style. We're going to have it, first of all, set up with the package core boot. their usual suspects. You're going to have your shell, you're going to have your basic things to get the system running. We're going to add two things. In this particular case, we're going to have PS Splash, which is actually part of the default one, but we also have drop bear. We want to have this image to have at least some SSH ability. And so drop bear is our chosen small footprint SSH agent. We're going to inherit, talking about inherit from before, all the other content from core image so that we make sure we have all the bells and whistles necessary to have a functioning image. And we're going to set a root FS size, kind of a default size of 181K. So I'm not really used root FS. I'm not sure the consequences of that particular choice. You can look that up, but that's what this is your basic recipe. And you would then, you already have YPP enabled in our build directory. You would edit, which we have done exactly like this. It's already been included because you did that step before in your BB layers layer. Okay, so you can build this image. Takes a while. If your SS state is up and running, if you already populated, it will take just a few minutes. I won't do that in this because I don't want to waste your time just watching my machine build. You can boot it with this command. I use slurp. I have a slide a little bit later explaining the difference between slurp and the default TUNTAP way to run QEMU. But let's have fun. Let's run that. So you can see that this is for real. Okay, here's my directory. Let me insert run QEMU slurp. That tells you use the user space version of a network connection. I will not have any graphics because I'm working over SSH. There's no separate window or shell that could be popped open to show you the content. And there's no graphics anyway, it's just a terminal. And I'm using serial input, and that will give me this. So I start QEMU. Here it goes. Booting up. Pretty fast. Small image. That's nice. You saw drop bear. It found drop bear and started it. Pretty cool. So I asked for it to have drop bear and it has drop bear. So since I had debug tweaks running, when I set up this project, I can just enter root and not have a password. That feature will be disabled in the next release, 5.2. There's documentation how you can get around that without debug tweaks. But here we are. And if we do which drop bear, it's there. So I created an image based on the core image base. I asked it to include drop bear. I built it. I'm running it here on QEMU, and drop bear is there. So pretty cool. So you just take that and start adding more recipes that are appropriate to this particular image that you wish to build, and you have your custom image that you can then send to your release team. Okay, let's come back to the presentation. Okay, so I did this with drop bear, found it. If we were using the graphical version of QEMU, which was the TUNTAP, you would see a splash screen that would appear on the boot. We didn't do that. As I said, we did the user space version of networking, which is Slurp. And again, I'll have a slide on that after the end. Yes. So let's talk about another tool to help for productivity and for exploring your content and building your first projects. This is the GUI for Yocto Project called Toaster. What is it? It is an HTML-based GUI. It's a way to create projects. You can use it to explore all the available layers, recipes, image, and machines to help you construct your first projects. It's also a way to build on a remote server. You can have one server running Toaster and have various people log into it and start building their content and downloading their images from that central server. And it's also a build analysis tool because after it builds the content, it captures all of the events that Bitbake produces describing all of the tasks, how long they took, what order they ran in, what disk IO, what dependencies were resolved. It captured all that and captured it into the database for that particular build so you explore exactly how it was built. And this is a way to capture the forensics of a build. So the two main users of Toaster are people, first of all, exploring what can be done with the Yocto project. They're not sure where to find stuff. They're not sure about the layer index. They like some guidance, like to help find stuff. This is great for that. In building, this is great for that. And then the advanced users where they're trying to solve problems. They have build issues, they have order issues, they have dependency issues, and they need to find those little needles in haystacks. So having ability to get at the build analysis data is very, very valuable. So now I'll be showing both of those. So this is what the screen looks like. You can have multiple builds happening at the same time. You have multiple people doing builds, keeps them all separate, and you can actually build against different releases at the same time. Toaster one slide. The first part, step one, they're all step one. Okay. The first step one is just, installing the regular release, nothing magic there. The second step one is you're going to want to do a virtual environment, and I'll explain why in the next slide. And then you install the requirements for Toaster, the Python requirements. The third step one is you start Toaster. You just source your project, and then you are able to source the Toaster environment. You start that, and it will instantiate the Toaster database and start the Toaster server. And then you can connect to it with your local browser, or if you use the web port, you can connect to it with a remote machine. And here are some of the answers. Why do we do V&V with Toaster? Toaster requires some specific packages from Python, most particularly the Django package, and it also requires some others to help do analysis and extracting web page content. And that can often collide with what the host has or what other users on your host may use. So by always using a virtual environment, you can ensure that you have the exact right versions of those modules, particularly Django, for that version of Toaster, so that you can make sure that everything runs correctly and you don't have to stomp on other people's feet. Why does it take Toaster a long time to start the first time? What it's doing is actually downloading the content of the layer index. We have a secret little API interface. And in fact, I'll just pop that open for you. Come over here. Let's move my things around. Add that URL. Here it is. This is the API access to the layer index, where we can then start downloading all the different content that we were able to browse earlier. So tools like Toaster are able to read this content, load it in. If you want to, you could read this content yourself if you want to get direct access and have machine-to-machine contact with the layer index in Yocto Project OpenEmbedded. So you can find out what the latest content is, what the versions, what the SHAs are, the licenses, is all here. So you can write your own tools against that. And Toaster is just one example of a tool that really able to leverage the content of the layer index. Please go full screen, and then I'll come back when I come back to the thing. Okay, full screen as requested. What is the web port option for? If you do not use the web port option, then it's going to default to only a local connection with HTTP and only use port 8000. If you use the web port and then set 0.0.0.0 as your web interface, it'll actually open all ports to all network connections to access the server, so that you can connect to this from other machines. And you can also say, I don't want it 8000, I want it like 8080 or some other thing. And you can have multiple instances of Toaster, for example, and just have each one start on a different port. As long as the ports are different, you can have all sorts of parallel Toasters. And we'll see in a second, when you build Toaster using Quilt Native, this is just mention, this is my sanity check. It's a first recipe, has no dependencies. It can build right away, and you can see, kind of make sure that whole Toaster thing is working. So let's go to the next slide. So when you boot Toaster, which we'll do in a second, this is the landing page. You can then start creating projects. And all you need to do is click on Create Project, enter a project name, enter the release you want to base it on. And then you can, number 3, you can actually you can change your machine. In this case, we're going to change it to QEMU ARM. And you can select which image recipe you wish to build, core image minimal. And it'll actually have previews of which images match that string. So you have type ahead. And when you do that, let's have a quick little demo of toaster access. So I come back to my, escape this, come to my browser. No, oops, I didn't want to do this one. Let me close this. I want my browser. Here we go. And I think I have a toaster already open. So this is Toaster. I started this on one of my servers. I'm on one of my Linux servers. I'm accessing it from my Windows machine, and other people can access it from their Linux host. I just use the IP of the server and use the port that I defined, which is 8000. And here is the home page after you start creating some content. So let's move this around. Let's do a new project. Based on a master. Let's do our new project. New project. Our new project. So if you have a command line project you've already created, you want to merge from there, you can create a toaster wrapper around that by this click here. You can base it on any recent releases. In my case, I'm just going to use master because I like living on the edge. So let's create a project. So this is the configuration page. From here, we can start changing things. For example, for machine, you can view any of the compatible machines. The machines are here. So these are all the machines that are available to you. 983. That's how many are available. Quite the number. Because we have a lot of people contributed many variations on all the different BSPs that have been supported over the years, Freescale, everything. So I'm going to make it easy. Let me just select one of the QEMUs. In fact, let me use a QEMU ARM, just like that. I could have used any of these others similar to that. Let's just use QEMU ARM. Distro, I could go with Poky, or I could change it to any of the compatible distros. Let's see what those distros are. There are 133. And just like the last thing, if I went to Tiny, I did a search, there's our famous 8. So yeah, very nice to look this up. And you can add these, but now you can even add those layers if you need to your project. Or you could just set it as is, Tiny Pokey, if you don't need any extra layers. So this is pretty cool. So not only can you select the distro, but you know which layer to add in this manner. You don't have to look it up. It will take care of it for you. So that's pretty cool. Go back to configuration. I'm gonna leave that alone. I don't need to add anything. I could add other stuff. Custom layers, distros. I could add Bitbake variables. Here are the core Bitbake variables. Here's that image install append. I could add more packages here, like the drop bear if I wanted to. I could change it as a state directory to some shared directory. Right now it's pointing, as you can see, to my project. Actually, it's to shared state. That's pretty cool. So you can do all that. So let's come back to the main page. I'm going to build something. Let's do that cool thing. Built up, type ahead. Pretty cool. So I could have done, for example, core dash image, and it shows you all the core image matches. So it's very nice type ahead. Very, very convenient. Let's do the quilt thing. Quilt. I can spell it correctly. Native. And this showed you the layer it came from. Build. So it's going to queue the build. And hopefully start parsing it. Huh, did earlier. Build queued. I must have done something to my machine. You come back to that in a little bit. Let's leave that running. Let's look at all the projects. I've done some projects before. Let's look at the, here are my projects I've done before. Let me look at all the builds I've done before. And a couple builds failed. I wanted to show you how they failed. If you have a failed build, it has an error. You can look at it. And this is one, my first build, and it failed. And the reason is host tools. I forgot to set up my host tools on my host. So there is the error straight from Bitbake. So yeah, so I figured that out, installed the host tools, restarted everything, and then my build started to work. Let's look at, I did a core image, the builds. I did a core image. Let's look at this one, core image minimal. You can see that it built based on QEMU ARM. This is when I did it. No errors, no warnings. I generated these 4 default image types, and the project that I ran it under was called test. We can take a look at that. So here's the second part of the toaster I was mentioning, the build analytics. So from here, I have all the generated image files, so I can download these directly um, and put them into my machine or share them with my other team. You can get the license manifest right like that. Over. Oh, nope, I guess not. I'll have to fix that. Okay. This is configuration. The tasks that ran, 4,262 are the tasks not executed because they're probably from cache. Recipes built, packages built. So a lot of content went into this. We can look at the tasks that ran. I mentioned you could see exactly which was connected, which was built, and what order. This is the order that this is the exact order that things were built. We can look at the filter. These are little filters here. What's executed, what's not executed. We can look at the cache attempts, which was in the cache, which was not, had to be built from fresh. This was a early build, so most of it had to be built. We can also look at the recipes built, and you can see the dependencies. Pretty cool. Pseudo-native, it has 3 dependencies. Here they are. It has 1 reverse dependency. This QEMU helper native depends on pseudo-native. So you can see forward and reverse build dependencies. That's pretty nice. And you can see, yeah, the licenses, GPL, LTPL. Very nice to kind of get a view of what's going on. The packages, these are what actually gets built and then included into the tarballs to make your image. Approximate size. So that's nice. And you can actually go into these and take a look at what they are, where they came from. This wrapper thing, their size is not very big, 289 bytes, very small. This is a recipe that built it, layer, version, master branch, layer commit that was built against. So you know exactly where it came from. And runtime dependencies. This one does not have runtime dependencies. Let's see if we can find one that does. Packages. Let's see, I think, let's try NetBase. No, this one does not. Anyway, you can see from here the runtime dependencies, which is very nice. You can also see the performance. So what took the most time? Let's go see. LLVM native compile, that took a tremendous amount of time. In fact, twice as much as what GCC took to compile. And in fact, more than, well, next one is the Yocto fetch. That's also a big, big, long one. I guess you always fetch. It's huge, I guess. It's because why it takes so long to fetch. CPU usage, what actually took the time to build. LLVM, again, native, took the longest time to build. A long, long time. Again, much more than GCC and parts of the kernel. Yeah, the kernel only took 5,000 CPU seconds to build, whether LLVM took many times more, 6 times more. Okay, and disk I/O. Let's see what took the most disk I/O. Not LLVM. LLVM is way down here, 1.9 gigabyte. GCC is a big one here. So GCC, more disk I/O, just takes much faster time to build. Interesting. So we can look at the configuration. Look at bitbake variables. These are all the bitbake variables that were defined. If you saw the bitbake -e that Jan Simon was talking about, this is that information live. And what's pretty cool here is that if I pop one like BB files, it'll tell you exactly how this was constructed, how all of the sets, question marks, appends were executed in what order. So if you have a variable that's, you maybe put a question mark in front of question mark assign, or you think you assigned it, but it didn't get assigned to the right value. And here in toaster land, you can see the exact order where things were applied. So you can see why something got overridden with something you may not have expected. So this is very cool way to get history on how things were built. So I think I've covered how you can build stuff. Let's see the build finish. I'm just curious. Oh, nope, didn't do it. I have to go back and look. I must have done something. Okay, well, it worked before. You gotta take my word for it since we have all these builds. Okay, I'll debug that later. Okay, that was a quick demo on Toaster. Let's come back to the slides. Make it full screen. So again, if there's any questions, just please unmute and ask them away. Oh, here's some questions in chat. From which Yocto release is Toaster part of? It's been part of Bitbakes for 10 years. So every release you can. Can you modify recipes from Toaster? No, we don't do that. That's a little bit beyond the scope. People ask for it, but once you start that, it can start getting complicated. If you think that'd be a valuable feature, we can certainly implement it. We just have to have a way to do live editing, with like perhaps an upload to your download to a local editor and then upload back to your local layer. We could probably do something like that. But that'd be an interesting feature request. Is it building within the virtual environment Toaster's running in? What Toaster does is that, yes, what it does is it clones the release that you asked for, and then it runs against that Bitbake version against that release, so make sure that it's apples to apples and not the wrong Bitbake with an older release. But yes, so it has a scheduler and it'll run it on that environment. So all the things you set up in that environment will run against, but it will definitely build against that release and that Bitbake, and then create a local build directory for that particular project. Okay, 2 questions. Okay, if any other questions, go ahead and unmute. Otherwise, I'll go on. And this is just a screen capture of some of the build analysis that I was mentioning. Can you use Toaster? There's a new feature where you can import a already built project into Toaster. I have not used that feature yet, but it's recent. I think the last release or so. Um, so Colin, I'll try to get that to you, that thing. You can always import that project with that import checkbox I showed you in the beginning and rebuild. But yeah, you don't quite get all oh yes. What the feature does is that the Bitbake event tree is captured to a file, and then Toaster can read that event tree. And that's how it can capture and recreate the build analytics. So the question is yes. And I don't remember quite the command for that, but yes. It's not hosted. There's actually we have a version of a container called crops that you can run on your host, your Mac or your Linux or your Windows host that has the entire environment for Toaster. So you can bring that in and run Toaster directly. But we don't do a shared toaster, um, but you can do this at home. You could have if you have a group at work and you want to have one shared server, you want to have one person maintain it and have a big server machine and have people do their builds there rather than their own perhaps small machines. That certainly can be set up, and you can make toaster to be product level. By default, it uses the Django server and SQL database, but you can migrate that easily to use Apache and what's that server? Postgres for all the full power and protection that it provides. Okay, thank you for the questions. Let's build an application. This is how you do it. Let's start with a hello world. So you write an application. We're going to write it in C. Take a quick drink of water. Create a recipe to wrap that application. Modify the image recipe to include hello in the image. And this is how we do it. Let's go to the next slide. Again, a C package. So we're going to create by hand a recipe core. Create a hello and create a file directory, and then we're going to put our hello.c file into that directory. This is a simple hello program that we'd enter in this hello.c file. Could not be simpler. Let's write the recipe. It will show to you. And see recipe. This is what you would edit to make a very simple wrapper for the recipe wrapper for that application. We'll just give it a name. The checksum of the file just to make sure Bitbake is happy that you got the right file. You're going to want to define a source directory and an unpacked directory. Now, I've done this where I commented out the previous syntax where you would just create work directory. Your S is your source directory, and you define it as your work directory. This is no longer allowed. This is obsolete in the last release or so. You have to put it in a different place. It just caused too many problems. So we just stopped allowing it. So you're going to find your S directory, which is your source directory, as a subdirectory under your work directory called sources, and your unpacked directory you'll assign to the source directory. So that everything is clean, everything's separate. So yeah, I just want to remind you, and I think in the previous slide I showed you, this is where this document is, whereas this change is defined. So you can look that up and see why we're doing it. And then simple compile, just C flags, your CC compiler, your C flags, your load flags, which are by default inherited or empty, hello C, and then install your basic install instructions. Create the directory and install the application. So then you modify your image recipe to not just do drop bear, but let's add in hello. So now we have our own personal custom image that has not only drop bear, but also has our little application called hello. And you can replace that, of course, with your own application to do all your weld and special value add things that your customers will love you for. Then you can build it, rebuild your image. It's going to include the hello world, and you go to town. So let me just demo that. I think I have my server still running. Let me jump over there. Let's jump to the server. So hello, I built this previously. Let me spell this correctly. Yep, there it is, user bin hello. And if I run hello, it of course says hello. So we've proven that this image that I built, custom image, does have the two recipes that we added, drop bear and hello. And pretty cool and pretty easy. Okay, let's come back to the slides. Full screen. No new questions. Okay, I'm going to show you one more thing and then we'll have some bonus slides after that. This is a tool that we've been using for a while that I myself enhanced. There's ways to do debugging on content. And let me just pop this open because this is a pretty valuable link. Oh, I can't use that. Okay. Yeah, this got converted into an image from a text. So look this up in the docs, the debugging manual, talk about all the different tools that can help you debug your content. And I'm going to show you just one of them. This the task expander, and this is the ncurses version. We have a one that's Q based, but not all systems have Q installed. This is ncurses. Everyone has ncurses. So that you can explore your dependencies. And what you do is you just say Bitbake, just use a graphical interface and use the tool task expander ncurses. You give it a recipe name, and then Bitbake will run its task dependencies against that recipe. The tool will capture that event stream, and then it will tell you the rest of the dependencies. So let me do that. Probably the next page. I'm going to copy the command, paste into the screen. Okay, so the leave QEMU, by the way, is a quick Control A, Control X, Control AX rather. And if you do it slowly, I've discovered it thinks you're trying to type something else, but here we are. So bitbake-g-u task expander ncurses against the recipe zip. Start with that. And if you notice, it says, nope, I need some colors. So all you need to do is follow this command and add colors to your terminal so that you can have a decent output. And let's try this again. So scanning Bitbake, and there we are. Here are the dependencies for zip. The first, these are in order of dependency. So the recipe QA is the first task that runs against zip. And you can see that it has no dependencies, but there are three recipes that three tasks that depend on it. Fetch. And if there's no outside dependencies, these can run in parallel to other packages, other builds, other tasks. So that's how all that parallelism in Bitbake is done. You have recipes that do not depend on outside recipes, just within themselves, so they can all be run in parallel. That's why you see a whole bunch of unpacks all running together, a whole bunch of patches running together. It's when you get to the configure that you start hitting some dependencies on the outside world about what the environment is, what other packages are present. So, but these first ones, they just run independent. So we can just run them as parallel as we can. So you just walk down this tree. So there's a bunch of recipe tasks that this is dependent upon. You got to have your cross compiler, you got to have glibc, you got to have sudo, got to have zip do fetch, which is the previous task. So, but the only thing that depends on it is to configure. You can just kind of walk. If you want to get more information, you can use the tab key to come over here. Tab key to come here, so you can explore each of these. Let's do the help. These are all the basic commands. The tab is used to jump between the three boxes. You can do a slash to get a filter. We'll use that in just a second. To select something to look at, you just enter the enter key. You can print the current list of dependencies with the P key, or capture it to a file. In this case, task dp depends underscore print.log. So you can capture all this content to a text file so you can take it and look at it at your leisure. You don't have to do screen captures and all that. You can also change the toggle, the sort order to alphanumeric, but task, recipe, enter depend order, that's the default ordering. So let's just press any key. So yeah, look at that. Let's explore something. I'm just curious. Let's jump over here to patch native. There it is. There's the dependencies. A lot of things depend upon this. This one depends on install tool, but there are things before that could have run in parallel with no problem with respect to that recipe, that task we just saw. Let's do search. I mentioned quilt native is the first recipe, a task that runs, recipe that runs. And yep, nothing depends on it. It does not depend on anything, only depends within itself. And there's going to be a whole bunch of stuff that depends on it when we get up to here. So these are all the things that depend on quilt native being in your sysroot. And how many things are there? There's just the A's, B's, everything pretty much depends on quilt native because they all do patching. Things that do not do patching do not need to have quilt, but all of these do. So So here you are. There's a tool to really jump around and explore the dependencies. If you have unexpected dependencies, if you have your own recipe and you're not sure why it's building ahead of time or it's not building in the right order or not sure why something's not picking it up as a dependency, here's how you can explore what Bitbake sees so that you can then debug your situation. And let's just quit. Okay, hope that was fun. I had a lot of fun writing that. Let's come back to the presentation. Full screen. Any questions? Nope, not yet. Okay, so there are trainings. These slides were originally written by the people, our friends at Linux Foundation, the training group, and you can find more information there. They have classes that they support, and there's also stuff happening in, here in Yocto Project. And remember, it's not an embedded distribution; it's a way to create one for you, custom-wise. So here are a couple hints and other resources. Working behind a network proxy, we have ways to get around that. I know Intel is very famous for strong proxies. Other people have very strong proxies. There's ways to do that. What's the best way to contribute? Let's come to that in just a moment, but that's a really good question. Okay, how not to. So these are instructions to help you get beyond that. To not use the same shell. Since we're using the source command to enforce your OE environment, you do not want to mix that with other projects. You always want to have a fresh shell for each project. So I'm always going between build directories. So I always do bash, then do the build directory, then I just exit to leave that environment and then open a new bash and a new project. So you always keep the variables separate. You do not want to mix your variables because weird things could happen. Another hints. Oh, project resources. Open source, they've all been done through open mailing lists. So that's the first way to start contributing. Find out what's going on. Join our mailing lists and hear the content and talk to the people who are actually the maintainers of the different projects. Public repositories is here. You can see where our content is. Bug reports are in Bugzilla here. I mentioned Slurp versus TunTap. These are the two basic ways to connect to QEMU. QEMU is going to want to have a network connection so that can talk to the outside world, so that you can talk to it. Slurp is the one that works with user space. It does not require root access, does not require connections to a device driver. Its disadvantages, though, are it has minimal documentation, requires some SSH. Ping is not available by default. But other than that, it's pretty cool. It's what I use primarily because I can do stuff. The reason I give this little fragment for SSH/config is that if you want to use tools like the dev tool, which is happening in the other class parallel to this one, that's how it does this connection to the target over SSH. And this is how you can define a connection called QEMU to your QEMU server. But as you saw, I just ran QEMU slurp, no graphic, serial directly, and we had a very fast direct connection. The default way to connect to QEMU is using a TunTap kernel device driver. Very simple to connect. It's a full feature network connection. Disadvantage is you have to have sudo access. If, for example, and I'll just show you, let me jump back to my little demo here. If I were to, normally could just do run QEMU. It'll find the device, it'll find the rootfs, it'll find everything for you. When I do it, however, it won't let me. I didn't run it with sudo. And even if I did run it with sudo, there's a file that says etc run QEMU no sudo. So the master of this host has said, no, you cannot run QEMU on this device with sudo. Just don't even try. So if you own your own device and you have sudo access, you can use the default. If not, run slurp. It's pretty cool. Back to the slides, full screen. Here's some more tips. This is a grep that people like a lot. It's a way to search for content in a relevant way, in a fast way. Skips all the hidden files, the dot files. Searching perfect for metadata. And again, you can see these slides, so you don't have to memorize this or do screen captures. These slides are available online. This is some examples of using this tool to find content. Here's also for you guys using Vim. You can get we have a syntax highlighter for Vim that's aware of Bitbake in this location. So you can enhance your Vim to highlight your content appropriately for Bitbake and recipes and such. And here's an example. You got your blues, you got your reds, you got your purples, violets for your keywords. So it's pretty cool. Okay, those are the end of the slides. How to contribute. Let's come to that question. The way you would start is, of course, go to the Yocto Project.org. Join the, in fact, here's a button right here, Community Contribute. Community values, ways to contribute, contributor guide. Let's take a look. Lots of content here. Part of it's training, part of it's knowing how to talk to people. There should be yeah, here's how to actually create patches and start sending them. So it's good to find out who's the maintainer of the layer that you're trying to contribute to. So you can maybe start a relationship with them. You can follow these rules, how to format stuff so that it'll look reasonable and meet their minimal requirements, and then you can start that. And there's also there's some defects we mentioned in the content here, a bit about Git Bugzilla. Let me find that, Bugzilla. Let me open that up. There are a couple of defects that are set aside for newbies that are I forget how you spell it. And perhaps it's in the guide. There are some newbie defects that we encourage people new to the project to try. They're not very hard. They're usually very easy to solve. They're easy to resolve. Um, so there, you can start with a newbie defect. That'll get you kind of practice, get a relationship with the maintainer, and then you can work on to bigger bugs. Here at Wind River, we usually start our interns on a couple of those. They get practice on how to contribute to the Yocto project. They know how to format patches, how to create the content, how to communicate those patches to the main list, and how to work with the maintainer. So that's a very good experience way to get into the process. Okay, new boards. Well, here we are, Yocto Project. Let's take a look. These are the docs. Let me come back to the top. Open our project documentation. Oh, I'm not sure how to get back there. Let's go back to just Yocto Project. Yocto Project, docs, docs and manuals, board support packages, developer's guide. Pretty cool. So this document describes exactly what you need to know, how you can do it, examples. So this is where you start. So read up on this, do a couple trials. If you come up to a thing that you just did not understand, some complexity of Bitbake or the board, there's a mailing list. You can then ping people to ask some questions. But this is the place where you start. And of course, we have the existing BSP layers that you can take a look at and really understand. And I think I mentioned, let's actually look since you ask. Let's push D dot dash slash Poky meta. We mentioned the meta directory. Let's look inside the recipes dash BSP. So here's a bunch of BSP directories. It talks about Grub, it talks about all these tools. So this is the kind of place you're going to start with to find out about the different boards that are around and how to configure the different parts of it. So yeah, start with something that's already built, see how they did it. That can give you a lot of advice, practical advice, how to do it yourself, in addition to the guide. Okay. Copy the slides, already posted. What are the best practices on what files to upload to a Git repository in order to work with team building, build image? What files to upload? Sergey, I'm not sure I understand your question. You would populate the layer with everything that you need, which is the recipes, any BB files, and go ahead.
Yeah, I was thinking about a project now where a team could build the same image on. So my question is, what are those files that we need to upload and save it? So local.com seems like one of those. Also the layers, custom layer seems like another thing to save on a repo.
So
Is that
what you
right?
would do, so if it were me, I would build a project that works. Then I would take the changes I made to local.conf and then create a new layer and put those variables into the layers.conf, the layer recipe thing, so that, or into the recipe that's within that. So it will inherit that so that the local.conf is clean. It inherits those necessary changes from the recipe in the custom layer.
Okay, so you will always do an local.conf on the image
So
instead of an.
there's no local.conf in an image file.
Okay,
Yeah,
so in the
but
recipe thing, no?
there's recipes. So yeah, you put your changes into recipes. And you may
Mhm.
have different flavors of the recipe depending on what part of the layer you want to invoke. Your layer could do a lot of different things. So you could have, in fact, if a layer is for a BSP, you might have 3 variants of the board. So you may have 3 recipes that enable different features for those different versions of the board. So you capture, again, you would first build it with your own project and get your own local.conf, but then you take those changes and put it into a recipe in the shared custom layer. So you capture that knowledge into recipes so that the person who inherits that layer and invokes those recipes gets those changes without having to modify their local.conf. And that makes everything stable, everything consistent.
Mhm. Okay, thank you. And those
Yeah.
layers will be a one repo for all the layers. It's a separate repo for each one, but it's the best practice here.
That depends how you organize your work. Um,
Mhm.
if it's a group, you might want to have all the layers in one repository. Just kind of group the work. It just makes it easier to manage. At some point, you probably want to get atomic and have separate layers. We at Wind River, we have about 100 layers, 100 Git repos for each of the different layers. Because they're so atomic, we try to keep track of them. That's just a business choice, and you can change your mind. That's just again, just a choice of how you do stuff. If you're small in beginning, you probably want to have one repository for all of your custom layers, just to make it easy. But as you get more complicated and sophisticated, you probably want to break them into separate, because then you can maintain them separately. I hope that
Mhm.
helps.
Yeah, thank you.
Bugzilla. Yeah, I'm trying to remember where that link is for newbies. Um, Let me go back. Let me see if I can find it. This is a test on me. Um, okay, Yocto. Let's see, I went to Bugzilla. Oh, let's go back to the newbie guide. Yocto Project. Contribute. Let's see if we can find the word newbie. Help new users. Nope, that's not it. New features. Nope, not there. Okay, let's try community. Get involved, contribute. Contributor guide. Let's check here. Or the word new. No, where is that? Gosh, I'm trying to remember where that is. Let me try a different route. I'm gonna cheat. Okay, calendar. Open.
I think someone put it in the chat. You check that.
Yes, and here it is also, the newcomer. They call them newcomer bugs. Yeah, I'm gonna paste this also, but thank you who found that. That's pretty cool. Yes, here the newcomer. Use a new word, too close to the project. So here are 10, 12 fairly simple defects that we don't have time to do, but it would be very nice to have. But these are excellent ways to practice developing. And again, for Wind River, we have our interns usually take a couple of these just to get experience with the open source community. And this page in general, the bug triage, this talks about all the different bugs that are happening, all the different groups, priorities. So you can see kind of what's going on, the high priority. Certainly, if you can help with any of these, that would be greatly appreciated. It usually falls onto the same 10 people, so it'd be great to kind of spread that out. Tim Orling, Ross Burton, Trevor Gamlin, very welcome contributors. Okay, let's see what other questions we have. Get involved. Oh, there you go. Thank you, Marcus. Newcomers, yes, thank you, Sesmeet and Rajra. Is Ubud also built with Yocto as a recipe? Well, let's take a look. Let's look at project, recipe. See if I can find U-boot. Without a dash. Nope, let's try U-boot with a dash. Nope, software recipes. Actually, I should have started here. U-boot. Okay, here's a bunch of U-boots. So yes, U-boot is a recipe. That's for Marcus. Okay. Any more questions? Okay, with that, I thank you for joining the beginning class. In the other room, we had some hands-on exercises. Those slides are available if you want to do that self-paced. Recordings will be available in a couple of weeks if you want to listen in on the conversation. And the next 2 days are our presentations, and we look forward to having you join us. And we look forward to doing that. So slides for this lecture, all of the slides are available. Let's come to that page. Let me go a long way around. You'll see Yocto Project Summit, talks. And then if you go to the schedule for the whole conference here at Pre-Talks, you can see all the presentations. If you click on the presentation, you can see the description. You can also see any attachments. So you'll see my slides both in PowerPoint format or PDF format. And again, that works for every single presentation. If you don't see any slides, you tell that presenter, get your slides up. I appreciate the support, because we often have to chase some of the presenters to get their content done. Yes. Okay, thank you very much, Daniel and Jellison and Matt. Okay, and thank you for being part of Yocto Project and participating in our summit, our virtual summit. Okay. We'll just hold for a minute and then we'll stop.
Thank you. Thank you a lot.
Thank you very much. Thank you for the questions. Were good questions.